Ian Stewart, GMAT math expert, tutor, and writer, and this video is part of a series of videos I'm doing featuring high-level questions that I've designed. This video is really not meant for everyone. It's meant for test takers who have already studied the topic and who are scoring at a Q40 level or above. So if that's not you, then just bookmark this page and come back when it is. My questions, they're not modeled after published official questions. Instead, they're much more like what you'll see on test day, questions testing the same familiar GMAT concepts, but in unusual or inventive ways. And the questions are quite challenging, so don't be concerned if you find some of them difficult. To get the most out of this video, you should try each question. I'll put each on the screen for 5 seconds, so press pause. But if you get stuck, don't spend more than about 90 seconds on any one problem. So if we label our missing angle, it's 22.5 degrees. And here, 67.5 degrees, that's not an angle we know anything about. Often when you see an unfamiliar angle like that, you want to divide it up so you do get one angle you do know something about, like a 30, a 45, or a 60 degree angle. And the number 22.5 gives us a clue about how we might want to proceed here. That's half of 45 degrees. And if we just draw a line within the triangle that splits the 67.5 degree angle into a 45 degree angle and another angle, notice we'll get a 45, 45, 90 triangle on the left. We can work with that. But notice also, if we label all of our angles, which is something we should always do, we also get a 22.5 degree angle at the top of the triangle as well. So we have an isosceles triangle on the right. We can work with isosceles triangles as well. So the 45, 45, 90, the two short sides are length 1, the hypotenuse is root 2. And then in the isosceles triangle, the root 2 is opposite a 22.5 degree angle. It's equal to the right-hand part of the base, so that's also root 2. And the length of the entire horizontal base of the big triangle is just 1 plus root 2. So you could draw a diagram here and figure out which configurations are possible. But if you notice, each rug has an area of 10, and we're covering the entire floor with these rugs. The area of the floor can only be 10, 20, 30, some multiple of 10. But the area of the floor, it's also its length times its width. It's 11 times W. And if W is less than 11, and 11W is a multiple of 10, well, W can only be 10. And if we know exactly how big the floor is, we know how many rugs we need. Statement 1 is sufficient. Statement 2 is not sufficient. The floor could be 1,000,000 feet long for all we know, so the answer is A. So this question was inspired by one of Robert Rauschenberg's 3-panel white paintings. And it's a pure ratio problem. We're not given any lengths, and we're asked to find a ratio. So the actual numbers don't matter. We can freely invent one length in the diagram if it makes our life easier. And so I would call the width of the painting 1, the vertical side, because then we can avoid fractions altogether, and then call the width of a panel W. And notice then we want to find the ratio of the length of the painting to the width of the painting, so we want to find 3W to 1. And now if we draw a diagonal of the panel and call it little d, and the diagonal of the entire painting and call it capital D, we can just use Pythagoras twice now. So 1 squared plus W squared is small d squared. We find the shorter diagonal, the panel diagonal, is equal to the root of 1 plus W squared. And then 1 squared plus, in brackets, 3W squared, that's equal to capital D squared. And then the diagonal of the painting is the root of 1 plus 9W squared. Just be careful that you square the 3 along with the W. And we know the diagonal of the painting is twice as long as the diagonal of a panel. So root 1 plus 9W squared is equal to 2 times root of 1 plus W squared. And when we square both sides, we learn 1 plus 9W squared is 4 times 1 plus W squared. Be sure you square both the 2 and the square root. And then when you rewrite that, 9w squared minus the 4w squared, we get 5w squared. On the other side, we get 4 minus 1 is 3, so w squared is 3 over 5. And w is root 3 over root 5. And finally, remember we want the ratio of 3w to 1. So that's 3 root 3 over root 5 to 1, which is the same ratio as 3 root 3 to root 5. But if you look at the answer choices, we want to make the first number in the ratio an integer, so we just multiply by root 3 throughout the ratio, and we get 9 to root 15 as the answer. If you enjoyed these questions, I've written 4 long problem sets full of high-level questions like these, along with a set of books covering all of GMAT math that teach my conceptual approach to the test, which is perfect for high-level test takers. And if you're interested in any of that material, you can just visit my website. The link is in the description below.